We're going to talk today about Diagenesis. I think the three people talking will probably have quite different perspectives on this. And so I want to talk first about a comparison between EGS and sedimentary aquifers as geothermal sources, and then go in from that with the lessons from that into talking about Diagenesis. And so the comparison really is with EGS, and of course, as people have noted, not much electricity comes out right now from EGS. But it's a fascinating topic to work on. It's a difficult topic to work on, primarily because of depth and the fact that the reservoirs you're dealing with are basically zero permeability matrix, all the permeabilities in the fractures, and so they're intensely sensitive to effective stress changes, and effective stress changes come from changes in temperature by quenching, changes in chemistry, and also by changes in fluid pressure as you inject fluids into them. So it's an intensely reactive system. The Rosetta Stone, I think, to understanding behavior is in terms of understanding the effective stresses and how those are modified by temperature, fluid pressures, and chemistry. And that impacts issues of recovery of fluids from them and heat from them in terms of fluid circulation rates, reactive surface area, and of course, sensitivity to induced seismicity. To look at the main parameters and the key questions, I think you can do it by looking at the heat rate. The heat rate you want to pull out of something is the mass flow rate, which is kilograms per second of whatever your fluid is, specific heat capacity, and the temperature. So you need a hot reservoir, you'd have flow through it, but you also need to get broad distribution of that flow to be able to access the heat that's in the reservoir. So some of the questions are, and this is my key slide in case I go on, which I invariably do, but so some of the issues are, if you're using native fluids, or introduced fluids, what does that do to the chemistry, and therefore will impact Diagenesis, which we'll talk about. The opportunity to be able to use different fluids if you're not using CO2, because I think this idea of using CCS and geothermal combined is definitely a low-hanging fruit in terms of being able to combine two technologies that are needed at a beneficial cost between them, as Mark talked about yesterday. Fluid transmission in EGS, you're talking about taking microdarcy rocks to millidarcies, as this plot shows for both Basel and I think salts. But I think the real issue is being able to get distributed permeability in addition to getting some permeability. So that might not be such a challenging issue for some reasons we'll talk about later in sedimentary aquifers. Thermal efficiency is related to heat transfer and also the conduction length from the blocks into the fractures in EGS. And you want it to be long-lived. You want it to run for 30 years once you've been able to develop this heat transfer area. And you don't want to be surprised by chemistry. And of course, at the same time, you want to avoid issues of induced seismicity. So comparing EGS reservoirs to, I didn't change that, to sedimentary, engineered sedimentary reservoirs, you can look at the differences in parameters. And I think some of the important parameters in terms of geothermal energy are here. Certainly, if you're looking at EGS, it's typically a fractured, non-porous regime, and probably you're looking at porous, perhaps also fractured. Porosities are very different. They're probably much, much less than 1%, both pre- and post-stimulation. Permeabilities are very different. You go from stimulation at microdarcies, maybe to millidarcies. 10 to the minus 14 is kind of the targeted number. And you're probably much larger than that in terms of millidarcy magnitudes in terms of these permeable reservoirs. The ratio between matrix and fracture permeabilities is huge in crystalline basement, and in porous rock, of course, it's 1, because it's basically, and this is one of the key parameters. The heat transfer lengths from blocks might be large, as Martin was talking about yesterday. In sedimentary aquifers, they could be grain scale, so they could be millimeter scale, depending on your sweep. And the amount of heat that's in the reservoir in the fluid versus in the solid, you can do a very simple calculation. It's basically related to the ratio of 1 minus porosity to porosity. So if you have 1% in your reservoir, then 100%, basically you have 100 times more heat in the blocks than you do in the water. And so you need 100 pore volumes through it to be able to sweep it. And it's, in the case of sedimentary aquifers, it can be closer to 2 to 1 if you have, say, 30% porosity. Chemistry, not going to talk about now. And in terms of feedbacks, because these are so pressure sensitive, because all of the permeabilities in the fractures, then EGS basement rocks are typically very sensitive to these changes in pressures and temperatures by quenching, and those would be less strong in sedimentary aquifers, I would think. And so that kind of guides our thought process in terms of dealing with this. The other thought process which is interesting, which revolves around this permeability versus sweep efficiency question, is to look at how you actually remove heat from these reservoirs, even in some kind of first order suggestion. So the first order calculation, you can look at the amount of heat that you get out of the solid from the blocks, which is basically Fourier's law, the amount of heat that you get by sweeping by advection, which is basically just an advective flux, mass flux times a heat loading. And if you look at the amount of heat you get out of these individual blocks that make up your reservoir versus the amount that you take in the fluid, you can look at the ratio of these two things. And the importance of doing that is that in a EGS reservoir, you have these big blocks surrounded by fractures. In a sedimentary aquifer, maybe you have blocks surrounded by fractures also, but you also have porous media. And so the characteristic size of your thermal reservoir that you're circulating fluid around could be millimeter scale versus meter scale. And so the reason to be able to look at these two together is you can actually look at how the sweep efficiency, how the reservoir behaves as a function of this one parameter, the velocity of flow, and one of the spacing of these fractures, the block size if you wish. If the spacing is very large, then you don't get heat out of it very effectively. Water can flow through the whole reservoir. It's basically at uniform temperature, and the drawdown in temperature in the reservoir is very uniform. And so if you looked at a snapshot along your flow path, it would change from this time temperature early on to ultimately no temperature time infinity. If you're looking at putting it in at the upstream end of a reservoir, which is a powder, you instantaneously get all the heat energy out of the powder, and you basically deplete a skin of temperature, which physically moves down towards your recovery well at this end. And so the time pattern that you see as a result of this would be for this very fine-grained material, all of a sudden you get temperature out, the reservoir temperatures all the way up to the end of your production period, then it would drop off to zero because you get breakthrough of this cold water because you've chilled all the material behind it. And for the case where you're cooling it down incrementally, you get this long tail. And you can look at these in terms of dimensionless parameters that look at this, albeit very, very simple model in terms of kind of steady state temperature with recovery and steady state advection. It's not all completely hogwash. It actually works in, if you look at it spatially as well. A couple of people, Paul and Kate, both looked at the Green Garden and Witherspoon solutions. If you plot those solutions in temperature recovered from the reservoir versus this dimensionless time, you get exactly that same plot that you have here to be able to look at the recovery temperatures. This would be the recovery temperature with time for the powder reservoir, very small fracture spacing, and it's a log time on here, so this really isn't a straight line anymore, but you see these curves representing this other behavior. So getting temperature out of the reservoir, heat out of the reservoir isn't a problem. And by the way, these are the data on there for both Rosemanoes, which is the UK system, and also Fenton Hill. So somewhere between a very finely fractured reservoir and a very large block reservoir. And you can look at them in different ways. So that, I think, is important in kind of informing our debate. So the mass rate of flow you get out of a reservoir by pushing fluid is important. It's important only that you don't want to have large pump costs. You don't want to have to put your pressures up so high that you frack your reservoir. But after you get enough fluid through, I think the important issues are that you want to be able to get around the creation of flow paths that short-circuit your reservoir. And that's one of the key issues, I think, certainly in EGS, but I think also maybe in these sedimentary aquifers. You like to have no feedbacks. Rick's simulation he showed on Saturday, was it, had no feedbacks in terms of permeability change. And you could argue that in his case, you could actually shut off portions of the recovery well to stop the early breakthrough of fluids. And these reinforcing feedbacks, which both Kate and Paul Morgan mentioned in terms of the Green Garden solution, you're much better off having 10 small fractures in terms of heat transfer versus one big fracture taking 10 times the flow, although you're not in terms of pump costs, so it's a trade-off. But I'm guessing that these reinforcing feedbacks are potentially very large in EGS and potentially smaller in sedimentary aquifers. So how does Diagenesis potentially contribute to those? Well, it'll contribute to what the initial porosity and permeability of the reservoir is that you tap, which you know when you go in there. And it will also contribute to how it evolves during stimulation and development, and also over the long term as well. So with that in mind, we'll talk a little bit about diagenesis. In fractures, you can imagine, or porous media, the behaviors are the same. The processes you have. You can dissolve material from the pore space. You can, by pressure solution, embed or intergrow these point contacts into each other by elevating solubility. And it's this process at the grain scale or at the fracture asperity scale which is going to control your behavior. So these are a couple of examples of some experiments over relatively short time periods in the laboratory, looking at evolution of, in this case, permeability or hydraulic aperture. So this is a big aperture, this is a small aperture. Flow fluid along here. Underbalance it with respect to chemistry, so it's undersaturated in terms of quartz, which this is a Novaculite core. And you'd expect that maybe porosity or permeability would increase as you etch fluid out. You see exactly the opposite. Permeability actually goes down as you increase the temperature from 80 degrees centigrade to 120 to finally 150. And the way you can explain that is that if you imagine, I won't back up actually, is if you imagine that the asperities holding that fracture open are actually being removed preferentially than free-phase dissolution. Similarly, you can also imagine that this is something Pat Dobson, who's in the audience here, is looking at boiling within a fracture. You get the opposite effect. You deposit components as a function of boiling off water, in this case I think for Yucca Mountain type situation, and you end up reducing permeability as a result of precipitation. So it matters where the fluid dissolves from, where it goes to as it's redistributed, and you have to understand something about that to make some predictions of what's going on. So in terms of diagenesis, the usual models that are used are in terms of chemical compaction. So you take these high stresses that exist at this point contacts of grains or asperities, you preferentially elevate the chemical potential, you dissolve material out of here into the pore space, and then in the pore space it's either advected out of the pore space or it's left in the pore space to precipitate. Don't worry about the equations, we won't care about that, but you can represent this behavior just by elevated dissolution by stress, Fichtean diffusion along this interface which has some water film in it, and then once it's in the pore space, either it plates itself onto the sides of the pore, or it's physically carried out of the system to the next portion downstream, where it might be taken out of the system in your production well, or where it's actually deposited and actually fills up porosity. So this is trying to represent with some data from Andy Hash, looking at taking a bead pack, elevating the stress up to 70 megapascals, sealing it so no water flows out, and you see that the porosity reduces from about 35% to about 28% over a portion of a year, half a year, say. And this is an attempt to be able to replicate those in terms of following this models of pressure solution. And you see also that you elevate the concentration in this closed system because you're increasing the chemical potential at those grain-grain contacts. And so the idea of any modeling, even with these lump parameter models, simple models, is to be able to take experimental data, match it with the model, but then instead of being able to take it out to 200 days, a portion of a year, you like to be able to take it out to much longer timescales and be able to predict this loss of porosity, which bottoms out. And of course, we know that most sedimentary aquifers don't have zero porosity, so there's some mechanisms that actually halt this process going on. And the process halts because the stress is spread over a growing area, so the stress, intergranular stress reduces, and the driving force that drives this behavior reduces as well. So the idea of modeling is to be able to understand how you can project this behavior under different conditions. A busy slide here, but the take-home points I think are this. One is that you can make predictions of how porosity would reduce over time. You can imagine how strain would increase over time as you compact it, and you can imagine how chemical concentrations in the pore fluids would change over time. If you have an open system where you wash fluids out, then you don't reduce porosity so much because you don't have that stuff to plate the grains and fill up the pores. If you have an open system, a closed system, the porosity is reduced much more because you have precipitation going on. If you change the temperature from a low temperature, I like Kate's comment the other day, cool, young and cool versus old and hot. We would all like to be young and cool. I thought she was talking about the demographics of the audience, but apparently she wasn't. But so in terms of if you change the temperature from 75 degrees to 150, then you notice that there's time scales from 3 years to 30 years, so it happens much more, 1,000 years to 30 years. It happens much more quickly when you increase the temperatures, and there's this difference between an open system where you don't reduce porosity so much and a closed system where you do. So when the flows through the system has some fundamental control on the behavior. If you look at using capillary models to plate onto the grains, you start reducing the pore volume that's here. Flow rate is proportional to this pore radius squared, just as permeability is a function of a length scale squared. And if you look at how permeability changes also with temperature, then again you see that in an open system, you would reduce permeability less than in the closed system, these two ones. And also in hot versus hotter systems, then the time scale changes from 1,000 years to 30 years to 3 years. So you get that kind of intrinsic scaling in the system. You see these behaviors not only in natural sandstones, the mechanism of making these basins, but you also see it in proppants, for instance. These are some experiments that we did in conjunction with Halliburton, looking at proppant embedment into the walls, I think, of Bray or Brady sand. The fracturing, and you can't see very well here, but actually most of the change in permeability is due to both intergrowths of this bauxite proppant, but also fracturing of the proppant, and also filling the proppant pore space with precipitated minerals in this particular case. And attempts to be able to link, for instance, measured strains that occur during the compaction phase over about just a bit more than a month into strains which you project over longer periods with different temperatures, hotter, cooler, coolest, and then use those to make predictions of how permeability will change over the same kind of time scales, changing by orders of 7 to 5, so maybe 20 or 30% reduction in permeability to be able to look at those. Of course, you can take those and you could model them in some ways if you have ideas of how the coupling between mechanics, the mechanical driving forces, and the chemical potential drives to be able to look at how evolution of permeability changes around a well in this particular case with time. I'm not going to dwell on what those are, but you can make predictions of that. You can also follow in terms of processes, in terms of looking at the behaviors that occur in systems. And typically, if you flush fluids through EGS systems, the sequence of behavior is you get the fluid pressure happens within days. It's propagated through the reservoir. The temperature effect happens over years, a few years, and the chemical effects happen even longer than that. So you get this progression of processes happening over the long period in reservoirs. You can look at the behavior. Our interest was in applying the same kind of pressure solution behaviors to fractures. Of course, you can do that, and this is some exposition of being able to do that. This is trying to fit data to that first set of experiments we talked about, where we had this change in permeability occur over these three temperature changes of 80 to 120 to 150. And of course, you can do that as well, should you so wish. And you can then look at the behaviors that you'd have as a function of, say, raising temperature. If you raise temperature, if you raise temperature, then what you get is that at the hottest temperature, you get the fastest response. At the coldest temperature, for given stress, you get the slowest response. Or you can keep constant the temperature and change stresses. If you increase the stresses, you get a faster response. And if you decrease stresses, you get a strong response. They end up at roughly the same permeability or aperture at the end, but you can modulate behaviors based on that. And so the interest in diagenesis is being able to look at that. The other issue that's related to this is related to dissolution and movement of minerals through the porous medium. And not completely unrelated to this idea of heat transport. So if you have fine-grained material close to the inlet, you sap the heat from that straight away, and then you propagate the hot fluids through the reservoir, but you basically removed all the heat from close to the well bore. You can use the same precepts to be able to look at dissolution and precipitation, or mainly dissolution, and its progress in reservoirs in terms of instabilities or instabilities. And so these are some interesting experiments. Don't worry about those previous expressions. These are some plexiglass plates, a fracture in the plane of the screen, in which you're introducing fluid at the top, which is reactive. And you dissolve material away, and by dissolving material away, you make the fracture larger, and that slowly propagates through here with time. If you do these experiments at a low velocity, a low Sherwood number or a Peckley-Damkohler numbers, if you're a chemical engineer, then what happens is you basically dissolve all the material here, and you saturate your water so that when it propagates through here, it's 20 minutes. I guess I'm getting way off. I will take 2 more if I can do that. And so, because this has ramifications at reservoir scale, If you saturate your material up here, then it's super saturated, it won't dissolve anything more, so you get a stable front moving through the system. If you pump it in much faster, then you don't saturate it here, you still have the ability to dissolve material further on down the fracture or through your reservoir, the reservoir scale. And so you have some important ramifications of being able to develop your own heterogeneity by feedbacks in terms of not a thermal short circuit here, but a dissolution short circuit, a wormhole in the short circuit. So that's all I wanted to talk about in terms of feedbacks on permeability. The other peripheral component is to talk about roles on induced seismicity. It may seem a little remotely connected, but certainly induced seismicity is an important issue in terms of EGS. It shut down the Basel project. These are plots of time versus the radius away from the wellbore that seismicity was seen at this particular project, with a large magnitude 4 earthquake ultimately shutting it down. Certainly you can follow that behavior with models, and that's some of Ghazal Azadi's work. In thermal reservoirs, Chuan will talk about this in his mini talk tonight. You can look not only at induced seismicity caused by the fluid pressure transient you have in the reservoir, but also as a function of the thermal drawdown you have in the reservoir. And so late stage thermal drawdown also gives you the potential to develop relatively some induced seismicity. And the relation with diagenesis is that if you're transforming minerals, I've only talked about very simple quartz systems, but if you're transforming minerals, then maybe it has some influence on the kinds of seismicity, either hurting you or helping you, I don't know which one. But the idea is that if you look at this plot of seismic moment, so magnitude 8 earthquakes, magnitude 0 earthquakes, shale earthquakes would be 2 magnitudes over, versus duration, then you have regular earthquakes, and you have slow slip, long duration earthquakes where you have similar amounts of energy released, but over not periods of seconds, over periods of months to year, like is going on in Cascade here. And the reason for that is that earthquakes occur because you have strain weakening. So you slip, the slip surface becomes weaker, it gets to go faster, and it nucleates and accelerates. It can't do that if it slips and gets stronger. And so if you can look at the transformations of certain minerals and look at how those minerals contribute to either velocity weakening behavior or velocity strengthening behavior as they're transformed, then maybe they can contribute in some way to being able to change the magnitudes of seismicity you have. I don't know whether it hurts or helps, but certainly you can look at the intrinsic stability of slip on different minerals. Some of these are the transition minerals from weathering of feldspars into clays, for instance. And the instability threshold below this line is strain weakening, so earthquake propagating below this line, earthquake, so seismic below the line, and aseismic above the line. So diagenesis has something to do with that. Induced seismicity has some influence on permeability, as we know from work on teleseismic events. Slip-on fractures doesn't always give you increases in permeability. Sometimes it creates wear products, which kill permeability, which also is relevant to our work on reservoirs. And it's a good job that I talked about my key points at the beginning, because I'm way out of time now, and I'm just going to leave that there for you now. Okay?